Rotavirus is a leading cause of acute gastroenteritis in infants and young children worldwide. While it is most commonly associated with severe diarrhea, especially in low-income countries, recent research has expanded our understanding of its impact. Scientists now recognize that rotavirus can affect various organs beyond the gut, including the nervous system, liver, and pancreas. This broader perspective has led to the concept of disease by rotavirus, highlighting its systemic effects. In this video, we will explore how rotavirus is linked to autoimmunity, the mechanisms behind this connection, and the role of vaccines in prevention. Rotavirus infection is nearly universal among children by the age of 5. In 2016 alone, over 258 million cases were reported in children under 5, resulting in approximately 128,500 deaths worldwide. The virus is highly contagious, spreading through fecal-oral contact, contaminated surfaces, and even respiratory droplets. While many infections are mild or asymptomatic, rotavirus can cause severe, dehydrating diarrhea, vomiting, and fever. The burden is especially high in low-income countries due to limited access to healthcare and hydration therapy. However, rotavirus affects children in all socioeconomic groups, making it a global health concern. Traditionally, rotavirus was associated mainly with gastrointestinal symptoms. However, studies have shown that the virus can spread beyond the intestines, affecting organs such as the nervous system and pancreas. This systemic dissemination explains why some children experience neurological symptoms like convulsions during infection. Recognition of these extraintestinal effects has prompted researchers to investigate other potential consequences of rotavirus infection, including its role as a trigger for autoimmune diseases. Understanding these broader impacts is crucial for developing effective prevention and treatment strategies. Autoimmune diseases occur when the immune system mistakenly attacks the body's own tissues. Normally, the immune system distinguishes between self and non-self, targeting only foreign invaders. However, when this tolerance is lost, the body can launch an immune response against its own cells, leading to conditions like celiac disease and type 1 diabetes. Multiple factors contribute to autoimmunity, including genetics, immune regulation, age, sex, and environmental triggers such as infections. Rotavirus has emerged as one of the viral agents potentially involved in initiating these processes. Researchers have proposed 4 main mechanisms by which infections like rotavirus can trigger autoimmunity: molecular mimicry, bystander activation, epitope spreading, and cryptic antigens. Molecular mimicry involves similarities between viral and host proteins, leading the immune system to attack both. Bystander activation refers to the nonspecific activation of immune cells in an inflammatory environment. Epitope spreading occurs when chronic infection damages tissue, releasing self-antigens that trigger an immune response. Lastly, cryptic antigens are normally hidden from the immune system but become exposed during inflammation, potentially leading to autoimmunity. Molecular mimicry is a key theory in understanding how rotavirus may trigger autoimmunity. In this model, certain viral proteins closely resemble human proteins. When the immune system responds to the virus, it may also target similar self-proteins, mistaking them for the invader. For example, the rotavirus VP7 protein shares significant sequence similarity with the human IA2 protein, a target in type 1 diabetes. This cross-reactivity can lead to the destruction of healthy tissues, setting the stage for autoimmune disease. Bystander activation model suggests that the inflammatory environment during rotavirus infection can activate immune cells that are not specific to the virus. This nonspecific activation can break self-tolerance, causing the immune system to attack the body's own tissues. Inflammatory cytokines and increased immune cell infiltration can perpetuate this response, leading to ongoing tissue damage and the development of autoimmunity. This mechanism is especially relevant in genetically susceptible individuals, where immune regulation is already compromised. Epitope spreading occurs when chronic infection leads to tissue damage, releasing new self-antigens that the immune system has not previously encountered. These antigens can then become targets, expanding the autoimmune response. Cryptic antigens are normally hidden from immune surveillance but may be exposed during inflammation, further increasing the risk of autoimmunity. Both mechanisms highlight how persistent or severe infections like rotavirus can set off a cascade of immune responses that ultimately harm the host. Development of autoimmune diseases is multifactorial. Genetics play a significant role, with certain gene variants increasing susceptibility. Environmental factors such as infections, diet, and even sex hormones also influence risk. For example, autoimmune diseases are more common in females, possibly due to hormonal differences or genetic factors like X chromosome inactivation. Rotavirus infection acts as an environmental trigger, particularly in genetically predisposed individuals, tipping the balance toward autoimmunity. Rotavirus is composed of 11 segments of double-stranded RNA, surrounded by a 3-layered protein capsid. The virus contains 6 structural proteins, VP1, VP7, and 6 non-structural proteins, NSB1 and NSB6. Structural proteins form the virus particle, while non-structural proteins are produced only during infection. Understanding the structure and function of these proteins is essential, as some are implicated in triggering autoimmune responses through molecular mimicry. Rotavirus primarily infects intestinal cells, leading to gastroenteritis. However, the infection is not limited to the gut. Systemic dissemination has been demonstrated, with the virus reaching organs like the liver and pancreas. This widespread infection explains the diverse clinical manifestations and the potential for triggering autoimmune responses in various tissues. The ability of rotavirus to breach the intestinal barrier is a key factor in its systemic effect. Rotavirus is prevalent worldwide, affecting children in both developed and developing countries. The highest mortality rates are seen in low-income regions due to limited healthcare resources. In temperate climates, infections peak during winter, while in tropical areas, cases occur year-round. The virus is highly contagious, and repeated infections with different strains are common, especially in the first year of life. This widespread exposure underscores the importance of effective prevention strategies. Celiac disease is an autoimmune disorder triggered by gluten in genetically susceptible individuals. In 2006, a study found that the risk of developing celiac disease was proportional to the number of rotavirus infections in early childhood. This was the first epidemiological evidence linking rotavirus to celiac disease. Subsequent research suggested that antibodies against rotavirus protein VP7 could cross-react with human transglutaminase, a key autoantigen in celiac disease, supporting the molecular mimicry hypothesis. Some studies support a link between rotavirus infection and celiac disease. Others have questioned the association. For example, a larger cohort study found no significant difference in rotavirus immune reactivity between children with celiac disease and healthy controls. This suggests that the relationship may be more complex, possibly involving nonspecific immune responses or additional environmental and genetic factors. Ongoing research aims to clarify these mechanisms. Recent theories propose that rotavirus may break oral tolerance to gluten through bystander activation. In this model, the inflammatory response to infection alters the function of intestinal immune cells, making them more likely to react to dietary antigens like gluten. This shift from tolerance to inflammation could explain why some children develop celiac disease after rotavirus infection, especially during the critical period of immune system maturation in early childhood. Link between rotavirus and gluten-related disorders has also been extended to non-celiac gluten sensitivity (NCGS). This condition presents with gastrointestinal and extraintestinal symptoms related to gluten intake, but without the specific biomarkers of celiac disease. NCGS is thought to have an autoimmune component, and rotavirus infection has been proposed as a possible trigger. This highlights the broader impact of rotavirus on immune-mediated diseases beyond classic celiac disease. Type 1 diabetes (T1D) is an autoimmune disease where the immune system destroys insulin-producing beta cells in the pancreas. Rotavirus has long been considered a potential environmental trigger, for T1D studies have shown that rotavirus infection can accelerate diabetes in genetically susceptible mice, and that certain rotavirus proteins share similarities with human autoantigens involved in T1D. This supports the molecular mimicry model as a possible explanation for the link between rotavirus and T1D. Epidemiological studies in humans have produced mixed results regarding the rotavirus T1D connection. Some research found an association between rotavirus infection and the development of diabetes-related autoantibodies in children. However, other studies did not confirm this link, instead highlighting the high prevalence of rotavirus antibodies in the general population. These findings suggest that while rotavirus may contribute to T1D in some individuals, other factors are also important. Experimental studies have shown that rotavirus infection can cause inflammation in the pancreas, leading to the exposure of beta cell antigens and activation of autoreactive T cells. The innate immune receptor MDA5 has been identified as a key player in this process, promoting both antiviral responses and pancreatic inflammation. Genetic variations in the gene encoding MDA5 are associated with increased risk of T1D, further supporting the role of rotavirus as a trigger in genetically susceptible individuals. Autoimmune uveitis is an inflammatory eye disease caused by immune reactions against retinal antigens. Recent research suggests that rotavirus infection may contribute to uveitis through molecular mimicry. In animal models, rotavirus peptides have been shown to resemble retinal proteins, leading to cross-reactive immune responses. This mechanism could explain why some individuals develop uveitis following gastrointestinal infections, highlighting the far-reaching effects of rotavirus beyond the gut. Dietary proteins, such as those found in milk, have also been implicated in the development of autoimmune diseases. Rotavirus infection can promote inflammation in the gut, potentially breaking oral tolerance to dietary antigens. This may lead to immune responses against both dietary proteins and similar self-antigens, contributing to conditions like T1D and uveitis. The interplay between infection, diet, and immunity is a complex but important area of research. Biliary atresia is a severe liver disease in infants, characterized by blockage of the bile ducts. The exact cause is unknown, but rotavirus infection has been proposed as a trigger. Studies in animal models suggest that rotavirus can induce inflammation and immune-mediated damage to the bile ducts, possibly through molecular mimicry and dysregulation of regulatory T cells. These findings highlight the potential for rotavirus to initiate autoimmune processes in organs beyond the gut. The research has identified antibodies against alpha-enolase, a liver enzyme, in both animal models and human patients with biliary atresia. Regions of sequence similarity between rotavirus proteins and alpha-enolase suggest that molecular mimicry may activate autoimmunity in this disease. Additionally, regulatory T cells have been shown to reverse disease progression in animal models, indicating that immune dysregulation is central to the pathogenesis of biliary atresia. Rotavirus infection has also been associated with other autoimmune conditions through molecular mimicry. For example, the rotavirus VP6 protein has been shown to cross-react with desmoglein 3, an autoantigen in pemphigus vulgaris, a rare skin disease. Similarly, sequence similarities between rotavirus proteins and the ryanodine receptor have been linked to myasthenia gravis, a neuromuscular disorder. These findings underscore the broad potential of rotavirus to trigger diverse autoimmune diseases. Two oral rotavirus vaccines, Rotarix and Rotatec, were introduced in 2006 for pediatric use worldwide. Both vaccines are live attenuated and have significantly reduced the burden of rotavirus-related hospitalizations and deaths. The impact of these vaccines extends beyond gastrointestinal disease, with evidence showing reductions in childhood seizures and other complications. The role of vaccines in preventing rotavirus-triggered autoimmunity is now a major focus of research. Concerns have been raised about whether rotavirus vaccines could themselves trigger autoimmunity, given that they contain similar viral peptides as the natural virus. However, large population-based studies have shown that vaccination does not increase the risk of developing autoimmune diseases like celiac disease or type 1 diabetes. In fact, some studies suggest a protective effect, with lower rates of these diseases observed in vaccinated children compared to unvaccinated peers. A prospective study found that the risk of developing celiac disease autoimmunity was reduced in children who received the rotavirus vaccine and were introduced to gluten before 6 months of age. This was the first evidence of a positive impact of vaccination on the development of an autoimmune disease. Follow-up studies in Finland confirmed these findings, showing a lower prevalence of celiac disease in vaccinated children compared to those who were not vaccinated. Similar protective effects have been observed for type 1 diabetes. In Australia, the introduction of the rotavirus vaccine was associated with a 14% decrease in T1D cases among children aged 0 to 5 years. A U.S. cohort study reported a 33% reduction in T1D risk among vaccinated children, with the pentavalent vaccine showing a stronger effect than the monovalent vaccine. These findings suggest that vaccination may help prevent the onset of autoimmune diabetes in susceptible children. Exact mechanisms by which rotavirus vaccination reduces the risk of autoimmunity are still under investigation. One hypothesis is that vaccination prevents natural infection and the associated inflammatory response, thereby reducing the likelihood of breaking immune tolerance. Unlike natural infection, the vaccine does not induce strong intestinal inflammation, which may be key in avoiding the autoimmune trigger. Ongoing research aims to clarify these protective mechanisms. Long-term follow-up studies are essential to fully understand the impact of rotavirus vaccination on autoimmune disease risk. Recent research from Finland, with up to 14 years of follow-up, continues to show lower rates of celiac disease and no increase in type 1 diabetes among vaccinated children. These findings provide strong support for the safety and potential additional benefits of rotavirus vaccination beyond preventing gastroenteritis. Given the accumulating evidence, health authorities recommend rotavirus vaccination for all children, especially those with a family history of autoimmune diseases or genetic predisposition. The potential to prevent not only severe diarrhea, but also autoimmune conditions like celiac disease and type 1 diabetes makes vaccination a valuable public health tool. Ongoing surveillance and research will continue to inform best practices and recommendations. New rotavirus vaccines are currently in development, aiming to improve efficacy and broaden protection. These next-generation vaccines will need to be evaluated not only for their ability to prevent gastroenteritis, but also for their impact on autoimmune disease risk. Understanding the mechanisms of vaccine-induced protection will be crucial for designing safer and more effective immunization strategies in the future. Introduction of rotavirus vaccines has had a profound impact on global child health, reducing hospitalizations and deaths from severe diarrhea. The potential to also lower the incidence of autoimmune diseases adds another layer of benefit. Public health programs should continue to promote vaccination, monitor outcomes, and support research into the broader effects of immunization on immune-mediated diseases. Summarize, rotavirus is a common childhood infection with the potential to trigger autoimmune diseases through mechanisms like molecular mimicry and bystander activation. Vaccination has proven effective in reducing both the burden of gastroenteritis and, potentially, the risk of autoimmune conditions such as celiac disease and type 1 diabetes. Ongoing research continues to shed light on these complex interactions, guiding future prevention and treatment strategy. Researchers are actively investigating the detailed mechanisms by which rotavirus infection and vaccination influence immune responses. Studies are exploring genetic susceptibility, immune regulation, and the role of the gut microbiome in shaping disease outcomes. These efforts aim to identify new therapeutic targets and improve vaccine design, ultimately reducing the global burden of both infectious and autoimmune diseases. Clinicians, understanding the link between rotavirus and autoimmunity is important for patient care. Early vaccination, monitoring of at-risk children, and awareness of the signs of autoimmune diseases can help ensure timely diagnosis and intervention. As evidence grows, healthcare providers can confidently recommend rotavirus vaccination as part of routine pediatric care, knowing it offers protection beyond just preventing diarrhea. Educating families about the benefits of rotavirus vaccination is essential. Parents should understand that vaccination not only protects against severe diarrhea, but may also reduce the risk of certain autoimmune diseases. Clear communication from healthcare providers can help address concerns and encourage vaccine uptake, contributing to better health outcomes for children worldwide. Despite significant progress, challenges remain. Not all studies agree on the strength of the link between rotavirus and autoimmunity, and more research is needed to fully understand the underlying mechanisms. Vaccine coverage varies globally, with some regions still facing barriers to access. Addressing these challenges will require continued investment in research, public health infrastructure, and education. Policymakers play a crucial role in supporting rotavirus vaccination programs. Ensuring equitable access, integrating vaccination into routine schedules, and monitoring outcomes are key strategies for maximizing public health benefits. Collaboration between governments, healthcare providers, and communities will help overcome barriers and ensure that all children receive the protection they need. International cooperation is essential for controlling rotavirus and its associated diseases. Organizations like the World Health Organization and national health agencies work together to track disease trends, share research findings, and coordinate vaccination efforts. These collaborations have already led to significant reductions in rotavirus-related illness and will continue to drive progress in the fight against autoimmunity. New research is exploring the role of the gut microbiome, environmental exposures, and novel vaccine formulations in shaping immune responses to rotavirus. Advances in genomics and immunology are providing deeper insights into individual susceptibility and disease mechanisms. These emerging areas hold promise for developing personalized prevention and treatment strategies in the future. Understanding how rotavirus triggers autoimmunity may lead to new therapeutic approaches. Targeting specific immune pathways, restoring tolerance, or modulating the gut environment are potential strategies under investigation. These therapies could complement vaccination and provide additional protection for those at highest risk of autoimmune diseases. Engaging communities in vaccination efforts is vital for success. Culturally sensitive education, addressing vaccine hesitancy, and building trust with local leaders can improve acceptance and coverage. Community-based programs have been effective in increasing vaccination rates and reducing disease burden, demonstrating the importance of grassroots involvement. As our understanding of rotavirus and autoimmunity evolves, so too will our strategies for prevention and treatment. Continued research, innovation in vaccine development, and strong public health initiatives will be key to reducing the global impact of both infectious and autoimmune diseases. The story of rotavirus serves as a powerful example of how science can inform and improve public health. Conclusion: rotavirus is much more than a cause of childhood diarrhea. Its potential to trigger autoimmune diseases through complex immune mechanisms underscores the importance of prevention. Vaccination has proven to be a safe and effective tool, offering protection that extends beyond the gut. By staying informed and supporting vaccination efforts, we can help ensure a healthier future for children everywhere.